Lesson 2, Special Triangles. The goal for this lesson will be to evaluate exact values of sine, cosine, and tangent ratios for specific angles. There are two types of triangles that will appear in your math courses that are known as the special triangles. We use them to help us determine exact values of certain trigonometric ratios, and you'll be able to do this without a calculator. The first of the two is known as the 45-45-90 triangle. A sketch of one is shown below. So notice that this is an isosceles right-angle triangle. And in the picture I have, it's not labeled. The really important thing though is that the two sides which are adjacent to the 45-degree angles have to be the same. This is a property of all isosceles triangles. You're welcome to label these two sides as whatever you'd like. Just to make things simple, I'm going to label them 1 and 1. It doesn't matter what you label them as long as they're the same. And now we can use this information to find the hypotenuse. To do this, we use the Pythagorean theorem. So c squared equals a squared plus b squared. C squared is equal to 1 squared plus 1 squared. I'm just substituting in the two sides. This then simplifies to c squared equals 2. And lastly, taking the square root of both sides, you get that c equals exactly the square root of 2. I'm just keeping the positive solution because a side length can't be negative. So therefore, if the two sides are 1 and 1, the hypotenuse has to be exactly the square root of 2. And I'll just give you a quick heads up of where we're going to use this triangle. Let's say, for example, you wanted to calculate tan of 45 degrees. Go ahead and enter that on your calculator and see what you get. I'll wait. So you should have got 1, but look at how the special triangle allows you to determine this. Tan of 45 is opposite over adjacent. So pick one of the two 45-degree angles. Let's say you work with the one in the lower left. The side opposite the 45 is 1, and the side adjacent is also 1. 1 divided by 1 reduces to 1. And that's the whole purpose of this lesson. We can use this triangle now to find exact expressions for sine, cosine, and tangent of various angles. The second special triangle is what's called the 30, 60, 90-degree triangle. And a picture of this is shown below. This one can be a little less intuitive, but watch how we go ahead and construct it. I'd like you to imagine an equilateral triangle, and I'm just going to extend the picture shown below to show you what I'm talking about. In the equilateral triangle that I've drawn, notice that all three of the interior angles are 60 degrees. And hopefully you can convince yourself of that because at the top we have two angles of 30 and 30 degrees which add up to 60. So this is definitely an equilateral triangle. What has to be true in all equilateral triangles? Well, the property that it has is that all sides are of the same length. So similar to what we did with the isosceles triangle, you're welcome to label the side as whatever you'd like. I'm going to actually label one of the sides as 2, and you'll see why in a moment. What this tells you then is that all sides have length 2. For the side at the bottom, the whole length is 2. But the line that goes down the middle, and I'll just highlight it over here to make it clear, That line is the height of the triangle, and because it's drawn at an angle of 30 degrees, it must cut the bottom side in half. So if the whole length of the bottom side is 2, that means half of it is 1. Now go back to the original 30, 60, 90 triangle that I drew. We have 2 of the 3 sides, and the only one that we need is the height of the triangle, which I'll label as x. We can now work with the 30, 60, 90 triangle to find that side. It's just from the Pythagorean theorem. So c squared again equals a squared plus b squared. Now c, the hypotenuse, is 2. So 2 squared equals 1 squared plus x squared. And now we just solve for x. This simplifies to 4 equals 1 plus x squared. Subtracting 1 from both sides, you get that 3 equals x squared. And finally, square rooting both sides, you get that x is exactly the square root of 3. And I'll just label it over here. That would be the length of the third side. So at this point, I'm going to erase everything I drew just to clean up the picture. And this is what the 30, 60, 90 triangle should look like. And there you go. That's what the 30, 60, 90 triangle looks like. I just wanted to show you where those numbers come from. And I'll show you an example of how we use it. Let's say you wanted to determine the sine of 30 degrees. Go ahead, please, and enter that on your calculator. And you should get exactly 0.5. But look at the picture. Sine of 30 degrees is just the opposite side divided by the hypotenuse. In our picture, the opposite side is 1, and the hypotenuse is 2. So we get exactly 1 over 2, which is 0.5. That's what your calculator told you. So I hope this shows you what the purpose of the 2 special triangles are. I know you can find the value of any of these angles on your calculator, but the purpose is to be able to determine exact values of certain trigonometric ratios without a calculator. Okay, let's move on. At this point, I'd like you to pause the video and fill out the table on your own. Use the special triangles on the previous page to determine sine, cos, and tan of 30, 45, and 60 degrees respectively. For now, please leave 0 and 90 degrees blank. When you're ready, click play to resume and we'll fill out the whole table. Okay, here we go. From the special triangles on the previous page, we'll start with 30 degrees. Sine of 30 degrees is exactly 1/2. Cosine of 30 degrees is exactly the square root of 3 over 2. And tan of 30 degrees is exactly 1 divided by the square root of 3. Sine of 45 degrees is exactly 1 divided by the square root of 2. It's the exact same thing for cosine of 45 degrees. And tan of 45 degrees is exactly 1. For 60 degrees, the sine of 60 degrees is exactly square root of 3 over 2. The cosine of 60 degrees is exactly 1/2. And the tan of 60 degrees is exactly the square root of 3. So in this unit, we'll be using the special triangles to figure out these exact values. For most questions that follow, please don't use a calculator to get a decimal. We're going to work with using exact values, very similar to what we did in lesson 1 of unit 3. Now, as for 0 and 90 degrees, you can think of these as special cases. The sine of 0 is 0, the cosine of 0 is 1, and the tangent of 0 is 0. Sine of 90 degrees is 1, cosine of 90 degrees is 0, and the tangent of 90 degrees is undefined. You'll get a calculator error, so this would be sort of like taking the square root of a negative number or dividing by 0. Your calculator can't do it because it's not a defined quantity. please make sure that you know the special triangles. I'm going to ask you to memorize them because they will definitely make an appearance again in grade 12 advanced function. Please try to resist the urge to use your calculator this lesson. We're going to just stick with using exact values. Alright, let's see how we use them. We'll get started with example 1. We're going to determine the exact value for each of the following expressions. Let's get started. We have sine of 30 degrees multiplied by cosine of 60 degrees plus the tangent of 45 degrees. So for problems like this, we use our special triangles. Sine of 30 degrees is exactly a half. Cosine of 60 degrees is exactly a half. And tan of 45 degrees is exactly 1. Please follow the BEDMAS rules. You have to multiply before adding, so a half times a half is 1 over 4 plus 1. And adding 1 over 4 plus 1, we'll need a common denominator of 4. This will give you a simplified answer of 5 over 4. Moving on, part B. Here we have the cotangent of 45 degrees, take away the secant of 60 degrees, plus the cosecant of 30 degrees. To do this, you're going to have to first use the rules we learned in lesson 1. Rewrite these 3 new trigonometric ratios in terms of sine, cos, and tan. So cotangent 45 is just 1 over tan 45. Secant of 60 degrees is just 1 over cosine of 60 degrees. And cosecant of 30 degrees is just 1 over sine of 30 degrees. And that's how we approach questions like this. Now just substitute using the special triangles like we did in part A. Tan 45 is 1. Cosine 60 is a half. Sine of 30 is also a half. So this reduces to 1. Take away 1 divided by a half. 1 divided by a half is 2. Plus 2 again. And now we simplify. 1 take away 2 plus 2 simplifies to exactly 1. We'll do a couple more. Part C, sine of 45 multiplied by cosine of 45 plus sine of 30. Alright, in part C, we're calculating sine of 45 multiplied by cosine of 45 degrees plus the sine of 30 degrees. Using the table above, sine of 45 degrees is 1 over the square root of 2 exactly. Same with the cosine of 45 degrees. And sine of 30 degrees is exactly a half. Once again, don't forget BEDMAS. You have to multiply before adding. So multiply the fractions, numerator by numerator, which is 1 times 1 is 1. And then we multiply the denominators. The square root of 2 multiplied by the square root of 2 is 2 plus a half. And finally, a half plus a half simplifies to 1. And lastly, in part D, this should look very familiar from lesson 1. Sine of 45 degrees squared plus cosine of 45 degrees squared. From lesson 1, you should already know what this will be, but let's prove it. Sine of 45 is exactly 1 over the square root of 2 squared. Again, cosine of 45 degrees is the same thing. When you square a fraction, square the numerator and denominator. 1 squared is 1, square root of 2 squared is 2. And once again, a half plus a half simplifies to 1. And that's how we do these types of calculations without a calculator. I'll just remind you again, please pay careful attention to how we're doing this because this will appear again in grade 12. Let's try an application question. Here we're given a triangle a lot of it is unknown, but we're told that the cosine of angle alpha is exactly the square root of 3 divided by 2. And we want to determine the exact area of the triangle below. Well, first off, recall, area is base times height divided by 2, or 1/2 the base multiplied by the height. In the picture below, the height would be this side here, and the base would be this entire side at the bottom. I'll just label it as so. So before we find the area, we need to figure out the base and the height. There's not much that's given to us, but there are definitely a few things you can infer. I'll show you what I mean. First of all, we were told that cosine alpha is root 3 over 2. Kindly remind yourself that the cosine of an angle is just the adjacent side divided by the hypotenuse. So literally label the sides as they are. The adjacent, which is the height of the triangle, must be exactly the square root of 3, and the hypotenuse must be 2. Once again, I'm literally just labeling the triangle according to the cosine ratio. One other thing, I'd like you to take a look at this triangle I'm about to highlight. I hope you recognize that this has to be an isosceles triangle because one of the angles is 90 and the other one is 45. So angle beta over here must also be 45 degrees. And therefore, if the height is the square root of 3, this side at the bottom, which I'll label y, must also be the square root of 3. That's just a property of isosceles triangles. Okay, we're almost there. We just have to find what this side is, and I'll highlight it over here. Once we get that side, we can add the two together, and that'll give us what the base is. So we can certainly find this side, which I'll label x, and that can be found from the Pythagorean theorem, because we have a right-angled triangle on the left over here. So using the Pythagorean theorem, c squared is a squared plus b squared. Please don't confuse that b with the base. And now we substitute, c would be 2. For a, we can plug in x. And for b, we'll plug in the height, which was the square root of 3. And now we simplify. This becomes 4 equals x squared plus 3. Because the square root of 3 squared gives you back 3. Subtracting 3 from both sides, we get that 1 equals x squared. And finally, square rooting both sides, we get that x equals 1. So I think we're just about done. The base now has to be exactly 1 plus the square root of 3. I'm just adding the two sides from the separate triangles. The height we determined was exactly the square root of 3. And now we plug it all in to find the area. So that's 1/2 of the base multiplied by the height. Remember, we're trying not to use calculators here, so let's go ahead and simplify just like we did back in Unit 3. We'll distribute the square root of 3 into the brackets. That's going to be root 3 plus 3. And aside from that, everyone, I'd say this is pretty much done. You can't really simplify this anymore. If you'd like, you can also write this as one big fraction. It would be root 3 plus 3 all over 2, because we're doing a half multiplied by the expression in the brackets, which is equivalent to saying take the expression in the brackets and divide by 2. And that's going to be a simplified final answer for the area of this triangle. Our last example of the lesson involves finding the exact value of the following. We're trying to find the exact value of sine 45 degrees divided by cosine of 30 degrees. I'll just write it out again here to give myself some room. So sine 45 degrees is exactly 1 over the square root of 2. I'm going to divide that by cosine 30 degrees. Rather than a fraction, I'm just going to write it out like this using the division sign to make it a little cleaner. You'll see what I mean in a moment. The cosine of 30 degrees is exactly the square root of 3 over 2. And this is why I did that. You don't really want fractions over fractions. Write it out like this, and what you can do now is multiply by the reciprocal. And this is going to simplify to a final answer of 1 multiplied by 2 is 2. And in the denominator, the square root of 2 multiplied by the square root of 3 is exactly the square root of 6. And that's going to be our simplified final answer. That's going to wrap up lesson 2, everyone. Please try the following questions for practice. And once again, I highly encourage you to memorize those special triangles. Thanks for watching the video. I'll see you in the next one.